In the second half of this set of lectures on imaging, we want to discuss magnetic resonance imaging or MRI. MRI is a huge topic. The topic of imaging in general is a huge topic, and one could devote an entire course to tomography and tomographic methods, as well as to MRI and MRI methods. And in fact, at Texas Tech, we do offer courses on MRI and MRI methods, as well as medical imaging. So, in this set of lectures, focusing primarily on an overview of the subject area as well as a little bit of a look at some of the instrumentation and systems that are involved. I've used for content on these slides the following references. I particularly would draw your attention to the second one on the list, which is the Siemens site. The instrumentation specifically is discussed on pages 181 to 205. The Wikipedia site, of course, is always good, always lots of good pictures there. And then specifically also this last site, which shows a lot of good photographs and illustrations of how an MRI lab and an MRI system is laid out. So clinical MRI, or clinical magnetic resonance imaging, is basically an imaging technique. It's used in radiology to form pictures of the anatomy, as well as some of the physiological processes of the body, both in healthy subjects as well as in disease. MRI scanners consist of a strong magnetic field. They use radio waves and they use field gradients to generate images of organs in the body. They don't involve x-rays, and that's what distinguishes it from a CT or a CAT scan. So there's no ionizing radiation present in an MRI. So what happens in MRI? Certain atomic nuclei are able to absorb and emit radio frequency energy when they're placed in an external magnetic field. Most commonly in clinical and research MRI, hydrogen atoms are used. They generate a radio frequency signal, or RF signal, that's receivable by antennas that are in close proximity to the anatomy being examined. Hydrogen atoms exist naturally in people as well as other biological organisms, and they're very abundant, particularly in water and fat. So most MRI scans are actually mapping the location of water and fat in the body. There are some other things that you can do, like look at the diffusion or movement of water directionally, which is kind of an add-on to an MRI scan and allows you to image different things, like directional tissues in the body. What happens is you have a background magnet, and then you have radio waves that excite what's referred to as a nuclear spin energy transition. These magnetic field gradients localize the signal in space. So by varying different parameters of the pulse sequence, which is the sequence of pulses that's given by the RF signal, you can look at different kinds of contrasts. And these contrasts occur because the relaxation properties of hydrogen are different for different kinds of observations, or you're observing it at a different period of time or under a different set of circumstances. So if we compare the MRI scan versus the CT scan, when you look at the X-ray radiation from a CT, a lot of that now has been minimized and pretty well controlled. But as far as MRI, there's no ionizing radiation. So definitely MRI is advantageous over CT in that regard. It's also widely used in hospitals and clinics for medical diagnosis, staging of the disease, and follow-up. It can yield different diagnostic information when compared with CT. However, it tends to take a lot longer time. It tends to be a lot louder, and it typically requires that the subject goes into a narrow confining tube. Additionally, if people have medical implants or medical devices, other non-removable metal in the body, they may not be able to undergo an MRI exam safely. And we'll mention this a little more later in the lecture. So here's an overview of MRI instrumentation. The major components include the main magnet. And the main magnet basically applies a strong magnetic field to the body and polarizes all of the magnetically susceptible molecules in the body. So um, it sort of sets the state for magnetizing the tissue. There are some shim coils, and these are present basically to correct any inhomogeneities in the main magnetic field. So basically, you have this long tube. The patient is lying here, and you have in magnets, you have end effects, you have fringing effects at the end. And so, because of that, if you were to go lengthwise, as well as you have effects because the magnetic field has some variation over the diameter. So, the shim coils are there to to counteract that effect. And then there's an RF system. The RF system is what provides the pulse, and then that excites the sample, and and it also contains the detectors that contain the resulting nuclear magnetic resonance signal. And then the whole system is controlled by one or more, usually at least two computers. You usually have one computer that's running the scanner and the timing of the RF pulses, and then another computer is taking the data as well as the patient data. And sometimes you even have a third computer if you're doing a functional MRI. You have a third computer that's providing some kind of stimulation. This is what a typical MRI control room layout looks like. This is the MRI magnet. The patient's oriented in this direction, vertical on the screen. You have basically 3 to 4 areas. You typically have the MRI scanning room, and then inside the scanning room there's an RF shielded door. It swings out and away from the console. In the MRI scanning room, you don't want anything metal because it can become a flying projectile object due to the high magnetic fields. You don't want anything that could be damaged by high magnetic fields. So pretty much in the MRI scanning room, there's just the scanner, and then sometimes you will have additional coils that are used for very localized or specific scans, as well as additional linens and other things like that. Sometimes cleaning materials are present there. Then there is an MRI system component room, and this is where your power supplies and your cooling systems, plumbing, things like that are stored. And then there's an MRI control room, and this is where the technician sits. The computers are in here, and there's a window here where you actually have line of sight of the patient or the volunteer that's undergoing the MRI. So really a minimum of 3 rooms, one for control, one for system components, and one for the scanner. So if we look, and this is from the Siemens site, so it's maybe a little bit slanted towards Siemens systems. There are 2 main manufacturers of MRI systems, GE and Siemens. Both are very good systems, and they mostly share a lot of things in common. So if we kind of go step by step through some of the different components of the MRI instrumentation, the first thing is you have the system that provides the main magnetic field. You have 2 kinds of magnets, permanent magnets that have a magnetic field strength ranging from 0.01 to 0.35 Tesla, and these are rarely used. And then you have superconducting magnets that have field strengths between 0.5 and 3 Tesla. These are common in today's commercial systems. In research systems, you can have systems that get up to 7 Tesla or more. Let me point out that this is an extremely high magnetic field. So the reason superconducting magnets have to be used is because of the level of the field strength. So a superconducting magnet is basically an electromagnet. A strong magnetic field is generated because you have electric current flowing in large coils. The conducting wires aren't made from copper. Instead, they're made from a niobium titanium alloy that's embedded in the copper. That's cooled to liquid helium temperatures. So it's important for me to point out here that you don't directly use liquid helium to cool. You basically almost always have a pre-cooling that's done with liquid nitrogen. When you take temperatures from room temperature to liquid helium, the mechanical stresses associated with that level of sudden cooling can be significant and can damage the magnet, and the reverse is also true. Should there be a power failure and suddenly the magnet and the magnetic system come up to room temperature too quickly, either due to a leak in the liquid helium or due to a power failure that interferes with the circulation of the liquid helium, then the damage can be catastrophic to the magnet because of the forces in going from being a superconducting magnet to a room temperature magnet. So the internal stresses on the materials are very severe, as well as just the overall thermodynamics problem. So this creates a homogeneous or close to homogeneous magnetic field in the center of the magnet bore, and the direction of that field runs parallel to the long body axis, like head to toe. Compared to an electromagnet, a superconducting magnet is energized only once to the desired field strength, and then you don't have to have any additional current supply to keep the magnet at its field strength because it is superconducting, so there are no losses. Ultra high field magnets. So currently, the optimal field strength for clinical imaging is 1.5 Tesla. So that statement is mostly true. It depends on how you define optimal. Here, remember, this is a commercial vendor's set of materials. So why is 1.5 Tesla optimal? Because of cost. Because while we're relatively sure high magnetic fields don't have any negative side effects, there is less experience in operating MRIs at 3 Tesla than at 1.5, so there's not a clear indication that there's no issue. However, as you go to 3 Tesla, you have some clear advantages. You get better image quality because your signal to noise ratio is considerably improved. You have shorter acquisition times because your field strength is higher and your signal to noise ratio is better. Um, and you have reduced motion artifacts. And it's more comfortable for the patient because a 1 hour scan becomes a 20-minute scan or a 30-minute scan. You also have additional detail enhanced exposures through higher resolutions and better visualization of processes that happen at the molecular level. So there are some systems available today that do reach the 7 to 8 Tesla level. Most of these represent the upper ceiling in MR, and they're currently used for research purposes only. There are a limited number of studies that have used this level of field strength with humans. However, it's primarily reserved for animal studies until the safety can be ascertained. So the other important aspect of the system are the shim coils. When you have large magnetic fields in a long tube, you're going to have both effects across the diameter as well as effects that occur at the ends, as well as effects that occur because you have a person in the system. In addition to that, you sometimes also have additional coils or instruments in the system, like RF coils and detectors, if you're trying to measure something very localized. So there are special coil attachments. For example, there are head coils that are used for brain imaging. In breast MRI, there is a special breast MRI setup that involves putting something additional into the core of the magnet. And so this means that there are things inside that can cause inhomogeneities in the magnetic field. The shimming allows you to ensure that there is as homogeneous a field distribution as possible. And so we have some numbers here that for superconducting magnets, the main field should vary by less than 4 parts per million within the measurement field, which is about a 50 centimeter diameter. So that's talking about the diameter, the variation across the diameter. So we're going to stop the video here so that the videos don't become too long in length, and pick up with the rest of the discussion on MRI in the third video of this series.